Good evening, everybody. My job today is to review problem 22 from homework number 8 when we dealt with the Pythagorean theorem. So the problem states a Pythagorean theorem for triangles other than a right triangle. Suppose we have a triangle that is not a right triangle. For example, consider this triangle A, B, and C. Now, if we drop a perpendicular line from the top vertex down to the side A, and we cut A into two pieces, A prime and A double prime, we would have this following picture. Turns out that there's a formula, A squared plus B squared is equal to C squared plus 2AA prime. So we're going to use the Pythagorean theorem for these two triangles on either side of this perpendicular line H to produce two equations. And we are going to manipulate one equation with the other. And notice that H squared term drops out. So then we're going to deduce this following formula, remembering that A is equal to the addition of A prime plus A double prime. Once we have proved this formula, we're going to show what happens if the angle between the sides A and B turns out to be 90 degrees instead of an acute angle of what it is now. And the question is, what result do you get, and are you surprised? So I went ahead and made a picture of this triangle with the perpendicular line H, and I labeled it from point A to point D, and I just added all the vertices of A, B, C, and D being the intersection of the perpendicular line from the vertex A. So then I went ahead and set out to prove and derive this formula. And so I restated it up here at the top that we are to prove this, knowing that, and that H is perpendicular to side CB, forming the two smaller right triangles. So I set about to use the Pythagorean theorem on both of the small triangles. So triangle CAD gives us, which I will go back to, so CAD is equal to A prime squared plus H squared equals B squared. This bigger triangle over here is going to be A double prime squared plus H squared equals C squared. So I wrote that out, which is located right here. So then I rearranged the terms so that H squared is by itself. So by subtracting A prime from B squared, or excuse me, A prime squared from B squared, we would get H squared alone. And then on the right-hand triangle, we would subtract A double prime squared from C squared to get H squared. So initially I had subtracted these two equations, and it didn't work out very well for me. So I went back and thought about what we teach our students in algebra is that if you have two equations equal to the same term, you can set them equal to each other. So that's what I wrote. Since both equations equal H squared, they can then be set equal to each other. So we're solving two equations by substitution. So here they are set equal to each other. And so we are proceeding to add and group like terms. So we added A double prime squared to both sides and subtracted B from both sides. So then we get both the A's, the A prime and the A double prime on one side of the equation, and C squared minus B squared on the right side. So I stared at the left side of my equation and I realized I had the difference of two squares. which allowed me to factor these. So then I proceeded to factor, so we have a double prime minus a prime times a double prime plus a prime, still equaling to c squared minus b squared. Now, they gave us that hint early on that we know that the full length of a is equal to a prime plus a double prime. So I subtracted a prime from a to get a double prime by itself. So I substituted both of these, a and a double prime, these values, into this equation up here. So if we look very carefully at the first term, we have a minus a double prime minus, a minus a prime minus a prime times just the quantity a from the substitution is equal to c squared minus b squared. So we simplify that. So we have a minus 2a prime times a equaling c squared minus b squared to distribute the a. Now we distribute it and we have a squared minus 2a prime, which is something we want, equals c squared plus minus b squared. So we rearrange terms one more time by adding a prime, 2a prime and b squared to both sides. So this moves over here and the b squared moves over here, and lo and behold, we get the a squared plus b squared equals c squared plus 2a prime, which is what we wanted to prove. So then the latter part of the problem asks the question, once you have proved this formula, which we just did, show what happens if the angle between the sides A and B is 90 degrees. Well, that sounded really fun, and I was trying to think of how I could represent that. So what I did is I went ahead and I built this triangle again, and I showed that we have the perpendicular from A down to B forming 90 degrees. And currently my C is at 45 degrees. So what I want to show with this is that we are to move point C so that the angle between A, C, B becomes 90 degrees. So I built this so that you can grab C and you can start pulling it along, and what happens is if the angle between line B and line A becomes 90 degrees, oops, missed it just a tad, that B will then become really side H. And I cannot get this to be 90. No matter how many times I practice this. So was this a surprise? Yes. Side B became the same as the perpendicular, which we all know that the perpendicular of a right triangle is the other side. So that was kind of really cool to have this animated. And I made a little YouTube video of this, of going from here to here. So thank you so much, and we'll see you the next time around. Have a good evening. Bye-bye.